So we have a few named particles. An alpha particle. Sorry, whatever this one. Its composition is 2 protons and 2 neutrons. Has a charge of +2. Effectively helium nucleus. It is a helium nucleus. And our symbol is going to be either the Greek letter alpha or helium isotope. Sometimes we will include the charge, not often. So H24, 2. Beta particle. Also ring. I think for the most part, summarizing this, so a beta particle is a high energy electron. Meaning it has enough energy to escape atoms and not stick to them. So it's a free electron. It has high energy though. Its symbol will be the Greek letter beta. So I slanted B with a little tail at the bottom. Or we use E for electron. The mass of electron we assume is 0. And this number down below, this number down below is the atomic number. What does it represent? What does atomic number represent? Number of protons. Each proton has a positive charge. So you could also say that if this had no electrons attached to it, it'd have a charge of +2. So even though this is supposed to be the atomic number, we have a little abuse. We put -1. This indicates that it's a negative charge of 1. You could think of this as being the charge of the nucleus or the charge of the particle. This is how they usually write an electron. You can either put alpha or beta. I would say memorize that these two are alpha particles, at least in the context of. So in nuclear chemistry, we don't concern ourselves with electrons. Hence the name nuclear. We only concern ourselves with the nucleus. We can have an electron strike the nucleus and scatter it. But in writing out equations, we usually deal with something like this. Having this -1 here also helps our math. Lastly, we have a gamma, and I'm going to put quotation marks, particle, and maybe a question mark. It's not really a particle. It's an it's a gamma ray. So gamma ray or gamma radiation. It's a photon of light. I'll put light in quotation marks. It's not visible light, you can't see it. So there's like radio waves, microwaves, visible light, UV light, X-rays. Gamma rays have the highest energy. It's an electromagnetic wave. Its symbol is going to use gamma, the Greek letter gamma. We'll put 0 and 0. So it has no mass, it has no charge. And because my handwriting is not the best, so there's a gamma. But this is computer print. So let me look up my handwriting. As you may know, the letter A on the keyboard is different from how you actually write it. So sometimes it's written like that, alpha like this. There's beta. Almost kind of looks like a Y. Alpha, beta, gamma. Alpha looks like an A, except for it has its little tails over here. We have fission and fusion. Fission is when the nucleus breaks apart. Actually, they break into smaller components. It uses fragments. Fusion is when nuclei, so nucleus is singular, nuclei is plural, come together to produce so when nuclei come together to make a larger nucleus. So fusion is when two nucleuses or two nuclei fuse together. Fission is when they separate. So let's look at some equations. and examples. Um, so here's a common reaction. How nuclear power plants work. We start with uranium-235, and we bombard it with a neutron. I will also, I didn't do this, there's another one, so this is a neutron. A neutron has a symbol of lowercase n. Its atomic number is 0 because it's not a proton, so it has a mass of 1. What happens is we get cesium 144, rubidium, I believe that's rubidium. Rubidium 90, and 2 additional neutrons. This 2 additional neutrons can go and keep hitting more uranium atoms, and we get a chain reaction. Note that this doesn't always have to be cesium and rubidium. We can also get xenon and strontium, or we can get boron and krypton. Sometimes we'll get 3 neutrons being produced, and so on like this. But you can see the chain reaction. If we have a whole bunch of uranium-235, we hit it with 1 neutron, there is a chance that these neutrons could strike multiple atoms, and they can continue producing more neutrons, and this will accelerate getting faster and faster. If you don't control this reaction, it can accelerate to the point where a lot of energy is released, and that's an atomic bomb. If you're able to prevent these neutrons from colliding to some degree, if you can, for example, when it produces 3 neutrons, block 2 of them, so that 1 neutron hits another one, and then that continues that chain reaction. So you're limiting it so that only 1 neutron is ever hitting, then you can make a nuclear reactor. This is how all the atoms in the universe are actually made. So deep in the sun, we have hydrogen coming together and hitting hydrogen. What ends up happening during this reaction is the sun reaction is way more complicated. Give you all an idea. You end up getting hydrogen 1 plus a positron, or hydrogen 2 plus a positron, and a neutrino. We won't be going into positrons and neutrinos, but it's still important to understand how nuclear equations work. And this can, so this is the main sequence of how stars use their energy. Is we start out with 2 hydrogen atoms. They, because of the temperature and gravity and pressure, they come together, collide. A positron, which is an anti-electron, a positively charged electron, and a neutrino fly out. Basically, what happens is a proton becomes a neutron, and we get hydrogen 2. Another hydrogen 1 atom hits this, and a gamma radiation comes out, and we get helium 3. So this proton attaches with this nucleus. And we can also have the reaction come over here and get another helium 3. The helium 3 and helium 3 come and combine together, and we now get 2 hydrogen atoms and a new helium atom. These helium atoms will eventually react, and we end up getting lithium, beryllium. So this entire periodic table is entirely made from hydrogen in the core of a sun. Have you ever heard the expression that we're all stardust? That's quite literally true. If you could look at every atom in your body, you could trace it back to the death of a star. Whenever stars run out of hydrogen, they start burning, trying to burn their helium, and but it's not as efficient. Eventually, a star will turn into a supergiant, and then it goes supernova and explode. During the explosion, it scatters out all these elements into the universe. While some of the elements either turn into a neutron star, or a black hole, or a white dwarf, or some other stellar physics that's kind of complicated. But for the most part, all of these elements all come from the fact that a lot of hydrogen decide to clump together because of gravity and form a star, and the star's gravity and pressure and heat eventually causes hydrogen to merge and make everything on the periodic table. At the beginning of time, after the Big Bang, there was only hydrogen in the universe. Everything else was created from a star. So, if I'm trying to think of any kind of equation. Usually I could just make this up in my head, but let's suppose that we had iron 56, and we combine it with nickel, and we get 1 atom later. What would this atom have to be? For the most part, we're going to assume that there is, so forever blank, that is the blank. There's only one item there. So 26 plus, so we can look at the atomic number. So this would be 28 plus 26 gives you 54. That means whatever atom has will be 54 protons. Looking up on the periodic table, we see that that is xenon. And what will be the mass number of xenon? One oh five. Hmm? 56 plus 59. 9 plus 6 is 15. 5 plus 5 and plus additional 1. So when these come together, it would be xenon. Would this be fusion or fission? This would be fusion. We have two smaller atoms coming together to make a bigger atom. All right, we have helium. What would go in this box? This would be hydrogen 3, tritium. So how did we come up with this? Well, we started out with 2 protons on the right, or on the left, so there has to be 2 protons on the right. So basically, if we look at just the bottom numbers, we have 2 equal 1 plus the box. Surely you can do this algebra. 1 plus only number is 1. Right. So we have 2 equals 1 plus, well, it has to be 1 there. And if we look at the top numbers, we have 2, or no, we don't, we have 4. Has to equal 1 plus whatever on the top. This has to be 3. And so our answer is 3, 1. So 1 corresponds to hydrogen. So it'll be hydrogen 3. And would this reaction be fission or fusion? It would be fission. So we're starting off with a larger atom that's breaking apart. Alright, let's do another example. So we have nickel. What would be in the box? So nickel is becoming nickel. What's changing? First of all, we again, let's look at the top numbers. Notice there'll be a top number here. So this arrow can be treated like an equal sign. So we have 59 equal to 58 plus the top number. And on the bottom we have 28 is equal to 28 plus the bottom number. So what's the solution for these two equations? So 58 plus 1 gives you 59. 28 plus 0 gives you 28. So we can go ahead and solve for the two numbers. The symbol we put here, so if you have a mass of 1, but not a proton, means you're a neutron. So some atoms randomly decay. So in order for, some isotopes are unstable. If they have too many neutrons, they will eventually break apart. One way they can break apart is by outputting a neutron or by decaying into a smaller element. For example, hydrogen-3 is mildly radioactive. It does not want to exist. So what happens is, sometimes it can either decay to hydrogen-2 and output a single neutron, or it can output to just normal hydrogen and output two neutrinos. Neutrons. So in this reaction, we have one proton, two neutrons, going to a proton and a neutron plus a neutron. In this one, we have a proton and a neutron, and we come up with a proton or hydrogen plus the two neutrons. So what would go in the box? 86 plus 2, 88, 224 plus 4, 228, 88, looking at the periodic table, corresponds to radium. And this would be fission. We have a larger element breaking apart into smaller components. We can have weird things happen too. So we can have a neutron become a proton. So let's do this example. We have 58, 28. So nickel 58, and this outputs an electron plus something else. So what would go into the box? So again, looking at, so let's do the top one. 0 plus 58 gives you 58. 28 is equal to negative 1 plus something. Copper. 29 plus negative 1 gives you 28. So what happens in this reaction is this is a neutron decay. A neutron output, what is, I often don't teach the true equations because a lot of these are unimportant at high school level. A neutron decay is when a neutron outputs a antineutrino, a proton, and an electron. I usually don't teach about the neutrinos and antimatter. Oh, I guess technically I do have antimatter. There's another one. A positron is the antimatter equivalent of an electron. We call this also a beta plus particle. Symbol. Plus, I believe. R 1 0 R E. It doesn't make any difference. For example, if I were to plug this in here, if nickel were to have undergone beta plus decay, a positron decay, doesn't make any difference. It still does the same thing. So what plus 1 gives you 28? 7. 0 plus 58 gives you that. Looking up at the periodic table, 27 corresponds to cobalt. And whenever things decay, what they decay into could also be unstable. This could probably decay. If this is unstable, then this will decay into something else. And it'll keep decaying until it reaches some stable isotope. So when dealing with radiation, looking back at the paper, when dealing with radiation, alpha particles are the least dangerous. They can be blocked by a single piece of paper and are at low energy. Because they're only a positive charge, basically the electrons in your body around your own atoms will block them. It usually can't penetrate skin too much, and usually have low energy when emitted. Beta particles can be blocked by wood and have medium energy. These particles, though, the electrons, they're known as free radicals. These electrons can attach themselves to atoms in your body and disrupt some configurations. So it could, remember I said earlier, valence electrons and atoms that determine reactivity. If you add an electron to the valence electron, it will change how the chemistry in your body works. And if these go in and attach themselves to your DNA, it can cause your DNA to work differently or break it apart or do something. So beta can be somewhat dangerous. Gamma, though, a few feet of lead or several feet of concrete, high energy. These things can be quite dangerous. Is anyone confused with how to solve these problems? And it seems straightforward. You just figure out the simple math. 1 plus 1 gives you 28. That'd be 27. Look up on the periodic table. 27 corresponds to what? Cobalt. This is the same thing here. The major difficulty is if I give you this. So if I ask you, if you solve the equation and you get 1 and 0, well, if you went to the periodic table and looked at the element with 1 as the atomic number, and you put hydrogen, this is wrong. Why? Because hydrogen has a mass of 1. This will be a positron. So you use an E bar, or not that way. This would be a positron. If I did 0 and 1, you did a 0 and a 1, you could memorize a neutron. Have a negative 1 and a 0. This is going to be a electron. There is going to be, let's see if I can make it a map. So this is not real. I try to use real nuclear decays, but this is going to be entirely fictional. What would go in the box? So we know the bottom number will be 0. So the bottom number is going to be, so we have 28 equals 28 plus 0. The top will be 58 is equal to 56 plus what? 2. So 0 and 2, there is no particle that has 0 and 2. The closest thing is 0 and 1 for neutron, and we just multiply by 2. So 2 neutrons. So neutrons will be the only. I think the only real exception is where we need to divide out, and we don't put two on top. Basically, if we get a zero down here, if we get a zero down here, it's guaranteed either a neutron or a gamma ray. And if we have a zero on bottom, it's either a neutron or it's gamma. And so if we get a 2-0, that's wrong. It should be 2 times 1/0n. So what would this be? This would be gamma. So again, nuclear really just deals with the nucleus. The nucleus doesn't change. What's happening is a high energy electron has attached itself to the atom, and now it just fell down into a lower orbital or lower energy level. And when it falls down to a lower energy level, it releases a photon, releases energy. I think that's where I'll stop. Uh, I was going to give out a worksheet sheet today, but I didn't print it off. And we'll probably work on a nuclear worksheet on Monday, and we'll probably go have a test Wednesday.